This is going to be an example optimization problem. Specifically, we're trying to maximize something in this problem. We're asked to find the largest possible area for a right triangle whose hypotenuse is 5 centimeters long, and we are also asked for the dimensions. The first thing we should do is draw a picture, and so that's what I've done. I simply have a right triangle. As you can see here, the hypotenuse is 5 centimeters long, and so we want to maximize the area here. I've labeled the two sides that we don't know. These are the dimensions that we want to find out, and so I've given them generic variables x and y. If you're curious what this looks like, I have a GeoGebra file, and it should help you visualize it a little bit better. Hopefully I've used it recently. Number 2. Yep. So I'll move this into the viewing window here. And as you can see, I choose to move the slider, and we maintain a right triangle. And yeah, and you can see how that changes the side length, the dimensions. Now, you can imagine, as we make the bottom wider, that's good because we want a wide triangle to have a lot of area. But the problem is it makes it shorter. And similarly, as we make the triangle taller, it makes it narrower. So you've probably already intuited the fact that we want to equalize these two, and I believe that's the correct answer. We want to try to find somewhere in there is going to be where our answer is most likely. Anyway, so that's what we're looking at. You don't have to create a GeoGebra file every time. In any case, what I want you to notice, just by looking at this, hopefully you automatically think of the Pythagorean theorem that x squared plus y squared equals 5 squared. Now, this is not the equation that we need to maximize. That's the area equation. But nevertheless, regardless of what we do with x and y, this is always true. So I'm going to solve this. Actually, we'll come back to that. We've got that in our back pocket. I'm getting ahead of myself. Okay, now what we have to think about is maximizing the area. Well, this is a triangle, so its area is going to be 1/2 base times height. So I'm going to go to the next page and just kidding. I'm going to go to the next page and here it is. This is the function that we need to maximize. Now, to maximize a function, we need to take the derivative, and this whole two variable business has got to go. We need to rewrite this as an equation in one variable, and so I'm either going to need to substitute in for the x or the y. Let's go back to the other equation. Okay, we know this is always true, and so we can solve it for the x or the y, and it's completely up to you. I think I've chosen to solve apparently for the y. So I went ahead and squared the 5 and then subtracted x squared and took the square root. Now, sometimes I get on you about, well, we need to consider the negative square root. Sometimes I don't. In this case, I'm not going to. I'm going to give you a second to see if you can guess why. Okay, the answer is because y is a physical dimension. You can't have a negative height of the triangle, so we're only going to consider the positive. But so on the next page, we had the equation in two variables. I'm going to replace the y with this, which is in terms of x. Okay, so now my area function is just in terms of x. I've replaced the y with the equivalent radical. And because I know I have to take the derivative of this, I've rewritten it with a power of 1/2 instead of a radical. We're going to have to take the derivative because that's what we do to find max or extreme values. All right, now this is a product rule situation. So I'm going to take the first guy, 1/2 x, and multiply it times the derivative of the second guy. So derivative of anything to the 1/2 power is going to be 1/2 that thing to the negative 1/2 power. I did this problem wrong for a while because I kept forgetting to then multiply it by the derivative of the inside. I forgot to use the chain rule. The derivative of the inside is going to be negative 2x. That's going to make a big difference. And then secondly, we're going to need the second guy times the derivative of the first. The derivative of 1/2 x is just 1/2. And then I've multiplied my constants, 1/2 times 1/2 times negative 2. So that's going to be negative 1/2. I put the negative on the top, I put the 2 on the bottom. I've got this x here and this x here, so I've got x squared on the top. And then instead of writing this to the negative 1/2 power, I put it on the bottom and wrote it inside the square root. For the second one, it's much easier. I have the square root on the top, I have a 2 on the bottom. All right, now to find the endpoints and the critical points. So the endpoints are obvious. I think so. Our variable is x. As we saw in the illustration from GeoGebra, the shortest this side can be a 0, the longest it can be is 5. So those are our endpoints. Now we need to find the critical points. Okay, so we're going to find the critical points. Here's our derivative. Now, hopefully you'll remember that critical points occur when the derivative doesn't exist. So maybe look at this and think about where it wouldn't exist. I can't divide by 0. I also can't take the square root of a negative. So perhaps you'll believe me when I say that if x is bigger than 5, I'm going to have 25 minus a number larger than 25, so I'd get a negative number. Or if it's less than negative 5. So if I have like negative 10, then that's going to give me a negative on the bottom or inside the square root, and that's not acceptable. The other situation we have to check out is we have to look and see what happens if the derivative equals 0. So I've just said, well, the derivative equals 0, and then I plug this in for a derivative. To solve this, I don't like that on the bottom, so I'm going to multiply everybody by 2 times that square root, and let's see what happens. I'm left with the negative x squared. Here, the 2 cancels with the 1/2, and the square root times the square root gives you what's on the inside. I'm going to combine like terms. That's what we've done here. I added 2x squared to both sides. I divided by 2, and then I take the square root. I'm going to remind you, as I often do, that the square root, we need to consider positive or negative. And just like with the y, we're only going to consider positive x's because it's the dimension of a side of a triangle. So we've got our x. Okay, now we had 3 points. One was the endpoint where x equals 0, so I plugged it in. The area is 0. That's not surprising. The other is the endpoint where x equals 5 and y equals 0. Again, the area is 0, and we're not surprised. The only other one to consider is at the square root of 12.5, and we get an area of 6.25. Technically, I should take the second derivative to find out if it's concave up or concave down, but considering the fact that these are both zeros and this is positive, I'm pretty sure this is a maximum. And so the final step is to interpret, and here we are. We just found out that the area is 6.25 when x is 3.536, and I grabbed this formula from the very beginning. I'm going to go back and show you. When we solved this equation for y, we have y equals this in terms of x. So here we go. We just plug it in. And you can do this in the calculator, but the math is actually really easy. This squared is 12.5. 25 minus 12.5 is also 12.5. And you have the exact same answer for x as you do for y. And again, as we saw in GeoGebra, we expected the answer to be somewhere around 3.5. And sure enough, it is.